Hello. In this video, I'll talk about very important algorithm that we use it most of the time in AI, deep learning, and machine learning applications, which is gradient descent. In previous videos, we saw how we could arrange multiple perceptron into two layers of network to overcome the perceptron limitation. However, we still don't know how to select the weights for this network. For example, W01. How can I calculate this? Wait. We will gradually build ourselves up to algorithms for automatically selecting these weights. And we will start with back propagation algorithm, and maybe there will be a fair amount of mathematical content. It might be hard to follow in detail. Instead, focus on the big picture. If you then want a deeper understanding, you can rewatch the video and pause at each equation to convince yourself that you understand everything. Let's revisit the concept of derivatives. In Arabic, we call it al-ishtiqaq, and how they can be used to solve optimization problems. Assume we have function y equals f of x. The derivative tells us how much y changes with a small change in x. That is, it's the sensitivity of y with respect to x. We can write this as y prime, f prime x, or dy dx. With a graphical chart, the derivative is the same thing as the slope of the tangent to a curve at a given location. As you can see in this curve, the slope tells you something about the curve. If the slope is 0, that is the tangent is horizontal, as you can see here, the red line. Then it represents a local minimum of the curve. And in everything, we want local cost. We don't want a lot of cost. So we search for this location. We will see how we use calculus to do that. If the slope is not 0, then it indicates the direction to move along the curve to get to lower value. Let's move on to two dimensions. In this example, y is a function of a vector x with two elements. X here equals to x0 and x1. This requires a three-dimensional chart compared to the two-dimensional chart in the last slide. For a two-dimensional function, we have two input variables, and we can therefore compute two partial derivatives. We have the sensitivity of y with respect to x0, and we have the sensitivity with respect to x1. When we take the partial derivative, we assume that the other variables in the function are constant. Let's have an example. Consider a function y equals a times x0 plus b times x1. If we now want to compute the partial derivative with respect to x0, we consider x1 constant. The partial derivative dy dx1 equals b. And it will be also the x0 constant when we calculate the derivative here, the partial derivative. We can arrange the partial derivatives into a vector known as the gradient. This is the gradient. And the gradient is denoted with a Greek letter nabla. This is one. This, we call it nabla. The gradient is a generalization of derivatives into multiple dimensions. We can compute the gradient for a function with an arbitrary number of variables. The number of partial derivatives will be the same as the number of variables in the original function. As you can see here, in our function, we have x0 and x1. So we have two derivatives, two partial derivatives, because we start with dy dx0 and x1 will be constant. Then we calculate dy dx1 and x0 will be constant. Now that we have reviewed the concepts, let's frame our learning problems as a mathematical optimization problem. Our neural network is a multi-dimensional function. Its input vector is x and consists of multiple values, x0, x1, x2, whatever our features are. So this is the input. The output value is y, which is a single value, also known as a scalar. The weights for this function are unknown. For example, here, we don't know the weight. Always we want to calculate the weights. So the weights are unknown. Neural network is a mathematical function, as you can see here. The task for the learning algorithm is to find suitable weights in a way so that given an input vector x, the function will return the desired value y. We will call the actual network output y hat. What we now want is that y, which is the desired value, minus y hat, which is the network value, equals 0. So we don't want any error. We can say that. If this difference equals 0, that means the network output y hat is the same as the desired value. That is, the network implements the desired function. So our target is we want y hat equals to y. Also, you can write it as y minus y hat equals 0. We will do this for multiple training examples, and we want the difference to be 0 for each example. The problem is that multiple errors might be in different directions and cancel each other. To address this, we can compute the sum squared errors. So we take the square instead of just the difference between y and y hat for each point. It is also common to divide by the number of training examples so that this is the sum does not depend on the number of training examples. The result of this is that we have a function known as mean square error, or we can say MSE. This is the MSE, the sum of I minus y hat I squared divided by the number of examples. You might have seen this in linear regression before. It's worth noting that for many neural networks, using the mean square error is not the best choice. We will see later in this section, but for now, it's fine to use this function. Note that the mean squared error function is always greater than or equal to 0 since we are summing up the squared differences. The task, therefore, is now to minimize mean square error rather than solving it for 0. A small mean squared error implies that the neural network output is close to the desired output. For the functions that we study within neural networks, it's often not possible to find an exact solution. Instead, we will use an iterative algorithm, which is the gradient descent. It is an iterative numerical method. It will find an approximate solution that is often good enough in practice. Gradient descent will find the minimum of a function as follows, and we show that in this figure. We start with guessing value x0. So here we are in x0. We start randomly. We will compute the gradient at this location, and since, as you can see in this figure, we are only looking at the single variable function. This is the same as just computing the derivative. We will look at if the gradient is close to 0. If that's the case, then we are already near the minimum point. If the gradient is not close to 0, then the gradient shows us in what direction to go, right or left, here or here of the curve. Also, the steeper the gradient, the longer step we want to take because the further away we are from the minimum point. So we will take a step in the direction of the negative gradient that's indicated by the orange line here. This one. The step size depends on the magnitude of the gradient. That will take us another point to the x1, which is our new guess for the solution. We again check if we are close, if the gradient is close to 0, and if not, we take another step toward x2 and another step toward x3, which is close to the location of the true minimum. As just stated, the step size depends both on the gradient value well as the learning rate. The learning rate is a constant denoted by the Greek letter eta, this one. Just like for the perceptron learning algorithm, I explained this in previous videos. Given an initial guess of the solution, xn, the next guess, xn plus 1, is computed by taking xn minus the learning rate, times the gradient at the point xn. This is shown in this mathematical formula. Let's consider this is in 2 dimensions. We know how have a 2-dimensional function. X is a vector consisting of x0 and x1. We make an initial guess for each of these 2 dimensions. So we have the vector x0 and x1. That puts us at point 1 in the chart. Here, this is our first step. We will compute the gradient in that point. The gradient is a vector with 2 elements. It's the 2 partial derivatives with respect to x0 and x1. We can then use this gradient to compute an improved solution, which is we take x minus eta times the gradient. That takes us to the point which takes 3 to the point 2 here in the chart. Again, we compute the gradient in that point and multiply by the learning rate and subtract from the current x, which takes us to the point 3, which is even closer to the minimum. Note that gradient descent generalizes to an arbitrary number of dimensions. The update rule will always be x minus eta, which is the learning rate, times the gradient. Now that we have seen how we can use the gradient descent to minimize function value, let's see how can we apply that to our 2-layer neural network. Let us first state the neural network as a mathematical function. We see that if you look at this equation from the right, we see that we have 2 weighted sum that are inputs to 2 sine function, this and this. These represent the hidden layer neurons. These 2 sine functions are then multiplied by weights and summed and used as inputs to the leftmost sine function. This represents the output neuron. This neuron is the input to an error function. For example, mean square error. We don't show the error function in this figure. If we can minimize this error function, then the network has learned. However, there are a couple of complications. When we want to minimize this error, we want to do this using gradient descent. However, if we look at this function, we see that it contains 3 sine. This and this and this. That will be a problem when we try to compute the gradient. In order to use gradient descent, we need continuous functions. As you can see here, this is not continuous. Also, even without these discontinuities, it's hard to figure out how to compute the partial derivatives for this function. We will address these 2 problems in the next video. Briefly, we will do this by replacing the sine function, which is also known as the activation function, by another function. and we will show how we can compute the partial derivatives using the chain rule of calculus. Thank you.